is a fully charged, boundless battery. Just like our sun, which is well known and understood to be an endless source of energy on which solar power depends, the Earth has a remarkably similar, renewable source of energy at its core that is both inexhaustible and ubiquitous. There are two heat sources originating from the Earth. The first is primordial. Radiating from the core of the Earth, it's as hot as the sun and came from the initial formation of the Earth over 4.6 billion years ago. The second is radioactive decay from the naturally occurring elements of the Earth. This heat, this energy, can be accessed with the many geothermal technologies humanity has today, and even more so with the advanced geothermal technologies developed just in the last few years. From just one section of the Earth's crust, when using these geothermal technologies, there is enough energy to power all of humanity for hundreds of thousands of years. There are plenty of wonderful technologies that have been developed over the years to access and utilize this energy. This video will step through several of these technologies and how each of their designs work and where they're best applied. By the end, you will see how geothermal, when made scalable, will change our world.
I guess we won't go through the whole thing, but it speaks to what we'll talk about today, which is energy, conservation of energy system.
While geo-exchange systems are very common and can be placed almost anywhere, they are not energy-producing systems. They require electricity, which is taken from the grid and used to power pumps, which pull heat from the Earth, just like using electricity to power an electric heater, but far more efficient. Traditional geothermal for direct heat use is a rarely used form of geothermal. It typically utilizes a hot, naturally permeable sedimentary aquifer, but sometimes can be done using igneous rock also. To produce heat, exploration is needed to find the right geological conditions, and wells are then drilled to extract brine. This style of geothermal is rare for two reasons. It needs the right kind of geological location, but that location also needs population density to consume the energy produced. A spa, or hot spring, is another type of geothermal many people think of. These are very rare instances of hot water from deep underground that flow to the surface along fault zones. These fault zones create natural pathways called fractures that allow water to flow to surface from deep underground. The connectivity of these pathways is referred to as permeability, the ability of fluid to flow through pore spaces or fractures in the rock. Where geothermal starts to really get interesting is when its energy is used to make electricity. Historically, traditional geothermal for electricity production requires a very hot hydrothermal source of water. Wells are drilled to extract brine from a naturally fractured reservoir, and then a heat-to-power facility is used to convert heat to electricity at surface. While it is a wonderful source of green and renewable energy, the subsurface conditions required for traditional geothermal systems are rare. It can be very difficult, time-consuming and costly to find and produce from these naturally occurring fractures. On average, the fractured zones do not have enough permeability to be viable for geothermal without intervention. Enhanced, or engineered geothermal systems, referred to as EGS, are new technologies growing in popularity, which could be used to increase the fractured nature of these low permeability zones. This allows for the permeability to be increased, thereby increasing the access to the hot rock. This is done by using hydraulic stimulation or fracking techniques. Alternatively, another type of EGS system uses thermal cooling of reservoirs by pumping cold water over long periods of time to stimulate and induce fracturing of a geothermal source rock. In situations where you have hot rock but no permeability, the intent of EGS is to fracture the rock and inject water into the formation, which flows through the fractures, then is pumped back to the surface for energy conversion. This technology is still being developed, but has the potential to make geothermal much more scalable while lowering the risk of investment. EGS is one of the few technologies designed to address geothermal scalability and could help take geothermal from the very rare to one day common. Several companies are working to bring this technology into operation now. It is important to remember that technological advancements making geothermal more scalable and widespread are central to the goals of all geothermal technologies. Accessing more and more of the Earth's natural battery, its energy, is going to be essential for geothermal to have a material contribution to the global energy transformation. All of the large-scale technologies we have covered so far still need some special, sometimes rare conditions to be viable, and most notably, all of these geothermal technologies are convection-based. For geothermal to be truly and globally scalable to change our world, something more is required. Everloop is a conduction-based system and is designed to profoundly increase geothermal scalability. Conduction systems are the critical and key difference to enable geothermal from the rare to almost anywhere and everywhere on the planet. Here's how. First demonstrated in Rocky Mountain House, Alberta, the Everlight facility has been operational since December of 2019 and is the full-scale proof of the conduction-based Everloop design, proving that a sealed-up closed-loop system to harvest heat using pure conduction is not just doable, but truly viable. Think of the Everloop as a super-deep, industrial-scale geo-exchange system. It provides highly predictable and reliable power, and the system can be tailored to the required output. This means the system is low-risk and predictable. Additionally, using the thermal siphon effect, which removes the drawdown of a parasitic pump load, dramatically increases the efficiency of the system. It essentially provides more electricity to sell. Geographically, for a conduction-based system such as an Everloop, there are no special conditions required. Everloops can be placed almost anywhere. This means it's scalable. Ever's 1.0 design, also known as the James Joyce configuration, is the commercial version of a demonstration facility. It uses a single drilling location for both vertical wells, meaning half the surface footprint of the Everlight facility. Once at depth, the wells turn approximately 90 degrees and then split into multilaterals to create more surface area for the working fluid to be in contact with the rock, therefore increasing heat extraction and overall efficiency. Through advancements in drilling technology, Ever is developing a 2.0 design, angling the multilaterals deeper into the rock to greatly increase overall heat extraction. This means it's stackable, which allows for more scale and power at a single location.
Well, I didn't mean to give you a party political broadcast here. This is put out by this company, and but it's relevant to what we're talking about today because we said that we would start talking about conservation of energy in the system, and so this is just an interesting journey through the geothermal story. So many of you might know of geothermal heat pumps with heating and cooling loops that are just either buried underground or with relatively shallow boreholes can be used to harness the 55-degree Fahrenheit heat in the subsurface just a few feet, maybe 10 feet down below our feet, as a way of heating or supplementing the heat that goes into a house by using a heat pump, which is just like a refrigerator. And it makes the point also that normal geothermal heat can be recovered in very specific locations. So on plate boundaries where the rocks are fractured up and where hot fluids are present high up within the crust, then geothermal reservoirs are active and can be used, like the geysers in San Francisco, 100 kilometers from San Francisco, on the San Andreas Fault, basically, or the Blue Lagoon here. If any of you have taken the Green Program trip to Iceland, but they're only in very specific places. So the other form of potential energy is this so-called enhanced or engineered geothermal systems, where you drill some hole down, you make some permeability in the crust, you know that you have a geothermal gradient of 25 centigrade or 50 centigrade per kilometer, so you're guaranteed to have heat, but you don't necessarily have transmission of fluids or fluids in that. And so if you can make a reservoir by rupturing it, fracking it, then you can use it as a big geological heat exchanger and do it anywhere, not just on the West Coast or in Nevada, where the plate boundaries give you very specific conditions. And then finally, this company, Ever, I think it comes from Endeavor, have this system of drilling down and connecting in the subsurface all of these complex laterals to have a conduction only rather than convection system. So the other methods are convection related because you pump in water, the water is the heat carrier, it contacts the rock and it comes up another borehole. But with this system, the water only circulates in the boreholes, doesn't go into the rock, and uses those boreholes contact area with the reservoir to be able to extract the heat. And they have a working system. This is in Rocky Mountain House, Alberta. I remember when I was your age, used to drive up through there at 10 o'clock at night on my way to jobs in northern Alberta. And it's a loop which is about 5 kilometers between the individual injection and recovery points. And if you link it up, you actually can inject in one point and recover through the same point rather than being 5 kilometers distant. And I guess they're making the point that they also have a plan to be able to do this for much more complex loops. Again, where the fluid doesn't contact the rock or permeate the rock, but is circulated only within the material within the boreholes. And so it involves less problems of induced seismicity and potentially is a scalable method. For me, the jury's a bit out on that still because conduction is a very inefficient way of getting heat into a system. And you don't have very much contact area between a borehole and the surrounding rock. It's a very thermally efficient connection in terms of insulating it, but not in terms of being able to pull the heat out of it. And so EVER is it's just a useful video that they have that I thought we'd start off with. But of course, that belies our point today of what we want to really talk about, and that is moving on to talk about conservation of energy. And so we'll start on a new topic today, and I'll make the case in terms of recapping exactly what we've kind of already done. And that is that if you look historically on what we've done in this class in terms of week 6, we had conservation of mass. You remember that we used this Reynolds transport theorem to be able to write some systems of equations for us. And we could choose the value of this parameter. And we chose in the first instance that we'd use this parameter is equal to mass. This parameter would be mass divided by mass, so equal to 1. And as a result of that, what we ended up getting for at least the steady state cases was that the sum of mass flow rates, so long as we attend to our rules of in and out, is equal to 0. This is the steady state one. You remember we also had a couple of extra terms on there, which were rates of change of density and rates of change of volume as our two other conditions that were put onto this. I guess if it was on this side, it would be minus because they all sum to 0. And so that was our week 6 stuff on conservation of mass. Last week, we switched over so that this parameter was equal to momentum. And you'll remember that for that, we ended up with something that was something like sum of forces are equal to sum of velocities times mass. That was our simplest form. This is just a scalar equation, one equation. This is a vector equation which has 3 components for our 3 different directions, but we typically dealt with one in isolation at a time. And I guess at the end of the class end of the week on 7.3, we did it for moment of momentum, and we just multiplied both sides through by a radius. And this radius gave us a torque, which was equal to this term on the right-hand side. So those are the equations that we dealt with so far. And so for all of these, we've taken losses, energy losses, are equal to 0. And we've managed to do that because we've assumed, just like Bernoulli, that the viscosity within our system is non-existent. It's not true, but it's perhaps not a bad relationship for us to be able to use to be able to get away with it. So now what we'll do is we'll talk about conservation of energy. So these were mass, momentum, now energy. And we'll use the fact that this parameter B that we use in Reynolds transport theorem is equal to two terms. One is total energy per unit mass and pressure over density. So this is total energy per unit mass. And if we do this and substitute this into this equation, I'm not going to do the derivation. I don't think it serves any purpose. The bottom line is that we get an equation that looks something like this. And I'll just write it out. And then I'll describe the terms. This is mass rate of change. And it will be internal mass plus pressure over density plus two other terms that you'll definitely recognize. And so this is internal energy. Per unit mass. This is velocity, this is pressure, this is elevation. So all of these other terms, pressure, velocity, and elevation, make sense in the Bernoulli statement. And what we will do is we'll define these two terms here as enthalpy. So H bar equals enthalpy per unit mass. So that's all we need to know. And so if we allow for this term to be this, then we end up with actually a very similar conservation equation. If I took out these two terms out of, so that the still the summation was there. It's a little bit like this term, a mass multiplied through by a quantity. In this case, it's not mass multiplied through by velocity, but by v squared. So this is kind of kinetic energy. So these terms are all energy terms. And we can use this in two ways. And I won't derive the expressions by putting it in here, but just note that we use it in two ways. One is we'll use it in a Bernoulli type way. One of you asked, I don't know if that person is still here, asked what the HP term was when we were dealing with some things before. And I said, don't worry about it. It's pump head. But what we've done so far is that we've written Bernoulli's equation in terms of an elevation, a pressure, and a velocity. So this is our normal Bernoulli term. But we've added to this another term which is pump head. Pump head is positive if it's a pump putting energy into the system. It's negative if it's a turbine taking energy out of the system. And I guess all that we need to know is that pump head is equal to, let's get back to using this. I know we use W in a different way. W is for watts, power divided by G times mass flow rate. So we can always relate this pump head. These terms are all units of length. And therefore this has to be in units of length. So units of length, we can do the conversion, joules, Newton meters per second divided by meters per second squared and kilograms per second. If you do the calculation, you'll find out that the units are indeed equal to length. And we can have another term here. So this is the upstream. We never worried before between upstream and downstream. Typically, we wrote point number 1 upstream, point number 2 downstream. But in all the cases that we've done so far, since viscosity was equal to 0, there was no friction, there were no losses in the system, so that didn't matter. But we have to write it now as downstream. I'll write it the other way around. I don't know why it's written this way here. And this is losses. These would be friction losses. HL is head losses, but it's really due to friction loss. And that is because now viscosity is not equal to 0. So as a consequence of this arrangement, we end up with a new form of Bernoulli, which looks like this. But more importantly, or not so importantly perhaps, we have a second kind of equation that comes from doing the same thing, which you'll see has the velocity squared term for Bernoulli. It has the elevation term from Bernoulli. But now it's switched out the pressure term with something which defines enthalpy. And so that is exactly this term here. So enthalpy includes the pressure term. So you can think of this second equation also kind of like Bernoulli. They're both one-dimensional equations, by the way, only looking between upstream and downstream. This is our mass flow rate, which we've called uppercase M, so kilograms per second. But now this term here includes both the pressure term, which is missing, right? Velocity squared, elevation, pressure. But it also includes the internal energy of the fluid that's flowing. And so that's useful, as we'll see. We'll do one nominal example today using a steam turbine, where you have steam coming in at a certain temperature, it changing its enthalpy by changing phase as it goes through the system. So you can bleed some energy from that phase change, and you can calculate exactly what that is. And this is the work which is done by the system. In being work into the system, so that would be pumping. And this would be heat flow in. Rate of flow of heat, rate of flow of work. Work rate, I guess. Heat, I guess, so this heat rate in, work rate in. Positive being, we'll have to have a sign convention for it. And so the easiest way to explain this, sometimes I don't explain things super well, is just to draw this idea of a streamline. And so this is the most, I didn't want to draw that. Yeah, then I can't draw. Oh, I can make it smaller, so fine. It's easier for me to write it out. Yeah, okay, fine. Yes, we have the technology, we can do that. So all I'm going to do is I'm going to draw a streamline, and that streamline now is a stream tube. And it has within that stream tube a pump. And it comes out the other side. And this would be our point number 1. This would be our point number 2. This would be V2, P2, Z2, etc. And all I'm going to do, we've seen this before, is I'm going to write a datum on there. This is Z1, and this is Z2. I'm going to go through all my colors. This is, they don't have to be horizontal lines, but I'm just drawing it because it makes it, we rationalize that they are horizontal lines if this is the same constant cross-sectional area as you go across here. So this is P1 over gamma, P2 over gamma, you're probably guessing what's coming. This is V1 squared over 2G, and this is V2 squared over 2G. And so you asked to be able to see this. So this is the upstream would be point number 1, right? The downstream would be point number 2. And we have an extra term on here. And the extra term is going to be, we've talked about this before, the energy grade line EGL, which includes the velocity. And we also talked about the HGL, hydraulic grade line. Hydraulic. And so my reason for doing this is that this term here, extra term here, we can think of, I wanted to do it black, no particular reason. You can think of it as this. So we have an upstream and a downstream. We have, on the upstream term, we have a pump head added. And on the downstream, we have head loss added. So you could think about this term being a negative term on this side. So these are the fact that by putting in a pump, we're putting energy into the system. We can work out what that energy is, but it gives us, elevates the energy in the system to this amount. And by coming across to this other side, we could think of this, I suppose, as being the energy grade line as we go across. So as a consequence of viscosity not being equal to 0, we have head losses in the system, and therefore we can deal with it in that way. So that's really what we're talking about today, and we'll be talking about for this week. So it's basically Bernoulli's equation with the ability to put energy into the system and to have energy taken out of the system. And this energy is just as a matter of fact. In fact, we can show it to ourselves, right? If we wanted to. We could think of this as P1 and P2. And so we have in our, if it's constant cross-sectional area, if A cross-section equals constant, then P1 minus P2 times area cross-section has to equal something that we've never considered before, and that is shear stresses that act on the inside of this thing, which we'll call tau. And that has to equal tau times area circumferential. So area circumferential equals 2 pi r times L, right? If this is 2r. So in other words, the circum is the area that envelops this fluid as it goes through here. And this is just saying that the pressure loss between upstream and downstream multiplied by the area of that pressure has to be reacted against by a shear stress due to frictional loss of the fluid multiplied by an area. So both of these terms are forces. This would be in newtons. And we've never dealt with this before because by definition, mu has always been equal to 0. So there is no shear stress for Newton's second law. So we'll come back to mu is equal to dv x dy. And so if we wanted to look at the cross-section across this tube, so if I drew a cross-section across here, the actual flow regime would look like this. And that is because at this boundary, there's a stick condition. The velocity is equal to 0. And this gradient in this velocity is this term here, which says how much force resists it. So we don't have to worry about that. But the bottom line is that in Bernoulli now, by including this term here represents this loss. So this term here we can think of as being equivalent to somehow to HL. Not the right units, because we said that pressure times an area is a force, stress times an area is a force. So this isn't units of length, but it's equivalent to it. And so that's what we're attempting to deal with. So that's it. So I won't derive those equations, but I will make the point that absolutely the one thing in the same vein as we had to remember from when we talked about conservation of momentum and conservation of mass, there was a very specific sign convention. Here the sign convention is you have to write it between upstream and downstream. The upstream term will always include the pressure on that side. The downstream term will always include the losses. And the essence of all the things that we'll talk about now, so I guess in week 10 and 11 we'll talk about pipe flows. Week 12 we'll talk about external flows around wind turbines. And week 13 we'll talk about internal flows of flow in ditches and rivers. All of those, the real behavior is conditioned on the fact that energy losses are real, and we need to be able to evaluate those if we want to do things like correctly dimensioning pumps to be able to get fluids through them, or correctly dimension turbines to figure out how much energy those systems can potentially give us. So that's it. So what we'll do is we have, just to reiterate, we have two equations. One is Bernoulli-like with a couple of extra terms. We just have to remember to write it between upstream and downstream. And the other one is kind of Bernoulli-like. But instead of Bernoulli in this term, we use enthalpy, which is equal to internal energy plus pressure over density. So if this was Bernoulli, we'd expect to have this term here for pressure, but we also have the ability to be able to include internal energy of the system. And it could be chemical reactions, internal energy in the system as well, if we wanted to. But we won't look at that. We'll just look at phase transformations. So that's it. So I won't bore you with the long-winded derivations to get to that spot. You can probably appreciate that you'll be happy not to go through that. But let's do a couple of examples. So I thought we'd do an example that relates to the energy side of the equation with enthalpy in it, and one related to the Bernoulli side of things, and we'll use the Bernoulli one. So I think today we'll go through a couple of examples. Wednesday we'll go through a bunch more examples, mainly on Bernoulli, and then on Friday we'll talk about how this relates to things in your major, such as flow in porous media for fluids, where the whole essence of that problem and understanding behavior is the energy loss that comes through permeability or hydraulic conductivity of the system. So that's it. So can I make this big? I'll make this big again, so you can see. So a very simple example, just comes out of the book. So the idea that you have a steam turbine with an influent fluid and an effluent fluid. You have a velocity coming in at 30 meters per second. You have an enthalpy that's given in terms of kilojoules per kilogram. It goes through the system and it comes out as a faster velocity, which you'd like because you're harvesting the enthalpy in the system, and it comes out as at a reduced enthalpy. You've donated enthalpy, if you like, to get velocity, and that velocity runs the turbine. And the question is, what is the output that you get from the system, in this case per unit mass? And so if we go back to the expression that we had before, we have these two expressions. We won't use the Bernoulli one, but we'll use the one that defines, again, this is just a one-dimensional equation, so it's between the upstream and the downstream. I guess the in and out would be point number 1, and the out would be point number 2, as you can imagine, getting a bit crowded. And it has this term which, instead of just being pressure, includes both the pressure and the internal energy defined as the enthalpy. And so we're just going to use that expression exactly. And so we can divide This is exactly that equation. Enthalpy, in minus out, velocity, in minus out, elevation, in minus out. If we draw a line through here, we have z equals 0, or z equals any number we want. The bottom line is that, well, they use the same terminology as me, or perhaps I use the same terminology as them, that the change in elevation is 0. We know that it comes in at 30 meters a second and goes out at 50. So this must be, goes out at 60, I guess, actually not. 60 squared. And they're asking for the work output, but per unit mass. So they don't give you a mass flow rate. So I guess what is done here is that this is divided through by mass flow rate. If you divide each of these through by mass flow rate, it's exactly what they're doing here. Then this is work done per mass flow rate by definition. And of course, we get rid of this term just as being equal to 1. And we have all the terms. We have the amount of enthalpy coming in. I guess it's 3348 and 2550. So it's 3348 and 2550. I guess we have enthalpy being equal to internal energy per unit mass plus pressure over density. We could look at the units of that for enthalpy. Pressure would be newtons per meter squared, and density is kilograms per meters cubed. So I guess that's Newton meters per kilogram. So that's joules per kilogram, which is exactly the units which are given here, kilojoules per kilogram. But the surprising thing, of course, is that that is equivalent to meters squared per second squared, right? Meters per second. And so it seems that the units of this don't quite match up because they're disparate from each other. So if we substitute these values in here, so this is just this equation, this term here is this term here is this, these two terms here are 30 minus 60. And then all that's done then to this second term is it's multiplied through by magnitudes of a joule per Newton meter. So this, I guess in units, is what's being done here. Let's not worry about this. This is just a conversion to get from 1,000 joules to 1 kilojoule. But this term is in terms of meters per second squared, right? These two terms here. If you multiply through by a joule is a Newton meter, so that's multiplying through by 1. And if you multiply through by a kilogram meter per second squared, this is just equal to, so this term here is by definition equal to a Newton. So a Newton divided by a Newton is still equal to 1. A joule divided by a joule is equal to 1. And then all that's harvested from this is the fact that joules per kilogram is taken out, and hopefully everything else should be able to cancel. So we get rid of a Newton, we get rid of second squared, and we get rid of meters squared per meter squared. So all you got going is multiplied through by that. So And it ends up being that the work coming out is equal to this amount, which is the amount of work you get out of it per kilogram, kilojoules per kilogram. Where actually the contribution of this last term is pretty small compared to the change in enthalpy in the system. So it seems a bit strange that we have to have these units of enthalpy, which are joules per kilogram, and those are equal to velocity squared over meters, but we can convert it into one another just by multiplying through by some terms which are equal to 1 individually. So that's one way of doing it. So I'm not sure that we'll mess around with that equation very much. More appropriate if you're taking thermo at the same time. This is kind of the spatial spatial extension, if you like, onto dealing with thermodynamics. But what we will do is we'll use this equation much more. And so one extra example to do today, and then we'll probably call it a day, and that is just to be able to make the case that there is no free lunch when you are dealing with frictional losses. So the idea of friction, I guess, is that friction always acts against anything you're doing. So if I drag this towards me, I have to expend some energy to do that. And I'm expending energy because I guess friction on the base is generating sound, perhaps you can't hear, and it's generating a small amount of heat. If I want to place it back to the location where it was, then I also have to spend the similar amount of energy to get it back, because friction acts to your left when it's resisting this movement, and it acts to your right when it's going back. And so fluids flowing, when they go in two different directions, do exactly the same thing. And so we've talked before about the idea that you could have, for instance, a pump storage scheme. And the idea is that you have water at some level. At nighttime, when you have your nuclear power plants running and no one to use the electricity, you use that excess electricity to be able to pump stuff up to a higher level. It sits here with its extra potential energy, and then when you need it at 7 o'clock in the morning to run your toaster, you just discharge it through here and back into the reservoir. It's kind of a closed system. It's a large-scale battery. And so I guess we could look at that in terms of when we're running hydroelectric power. And so when we're running HEP, we would be going from one location upstream to downstream. And I'm just going to write Bernoulli up here. And we said that we want to do this from upstream to downstream. So if we write Bernoulli for this, the only thing that's going to change is that if this is our large-scale reservoir, I'll write it as V top and V bot by definition are equal to 0. P top, you know this also, are equal to 0. And the only things that we've got are the elevations of these. And we know that we define elevations in terms of Z, and Z is just the difference between top and bottom. So this is what this is. So if you write it between, if we're running from upstream to downstream, from high elevation to this, then this would be Z1 plus HP equals Z2 plus HL. This is the amount of energy we'll get out of the system, so we want to know what we can make, so we can define this as HP. We can subtract this off to the left-hand side, and this would be Z2 minus Z1 plus head loss. We defined the pump head as being positive if we're pumping, but negative if we're using it as a turbine. So we could negative each side, and in which case this would be the energy from the turbine. So minus HP would be the energy from the turbine. Negative Z minus Z1, Z2 minus Z1 is negative, so a negative leaves this as a positive. So this is a positive number equal to the height separation minus the loss. And so the amount of energy we get out of the system, this is the amount of energy is negative HP, is equal to the height difference between upstream and downstream minus the energy losses by going through this. And so the energy losses would be from going through this pipe between upstream and downstream. If we run it in the opposite way, so running, I'm not sure what we'd call it, so charge the battery, I guess. Big geological battery. We write the same equation, but now we're going upstream. I guess we do it between 1 and 2 again. Perhaps that's confusing. So between 1 would be Z1 plus HP plus, equals Z2 plus HL. Again, we want to know the pump we get out of it. So again, I guess it'll just be the same expression. Z2 minus Z1. And now this is the pump head. So we've got no need to change the sign of this because positive pump is the amount of head we have to apply or the energy we have to pump. So we don't change this. This again is positive because we've written it upside down, right? Z2 is larger than Z1, so this is positive. And we have a head loss which we have to act against. So the amount of pump that we have to apply is equal to the head change plus a penalty because we have head loss acting against us. So the bottom line is that the head loss, the frictional losses, always act against the system. They're always a parasitic loss on the system. If we're running stuff through it, friction detracts from the amount of energy we get from this being a perfect system in delivering stuff here, and therefore we have a head loss here. And if we're pumping upstream as well, we also have friction acting against us. It always acts in the opposite direction that we're pulling, just like this. So fluid's no different from me pulling this across the table. I guess it would be more apparent if I was pulling this up on an inclined table perhaps, but it's exactly the same thing. And so that's it. And so this is the analysis they do, and they go through that. So I'm not going to say that anymore. So that's about it. So